First up today is going to be Brian Rasmussen. I should have practiced that before. He's with Texas A&M University. He is the Leland T. Jordan Professor II of Mechanical Engineering at Texas A&M University. He received his BS degree from Utah State University in 2000, followed by an MS and PhD degrees in Mechanical Engineering from the University of Illinois at Urbana-Champaign in 2002 and 2005. His research focuses on intelligent building and industrial energy systems. He is also the director of Texas A&M Industrial Assessment Center, which is where I first met him, a U.S. Department of Energy program that trains students to conduct energy audits for industrial manufacturing facilities. He is a fellow of American Society of Mechanical Engineers and a licensed professional engineer in the state of Texas.
It's a pleasure to be here today. Before I get started, I'm required to mention that the views I express today are not the views of my sponsor, the U.S. Department of Energy, who funded most of the things that you'll see here today, at least in terms of our research. But I'd also like to mention, as part of this, I am going to be showing pictures and things of particular commercially available equipment. Please don't take that as an endorsement or necessarily a comprehensive coverage. I'm not trying to play favorites with any brand. We just had to pick a few examples. So, just as context, so you understand a little bit of where I come from and my experience. As mentioned, I'm the director of the Texas A&M Industrial Training and Assessment Center. This is a national program. We have 36 centers throughout the country. We do no-cost energy assessments for industrial facilities, medium size, so anybody with utility bills somewhere between about $100,000 to $4 million a year are the facilities we kind of target. If you or any of your supply chain would benefit from one of our energy assessments, please let me know. We'd be happy to connect you. We have centers throughout the country. We'd be happy to connect you up to the center closest to you. We've been doing this at Texas A&M for a while. We've been doing it for about 40 years and coming up on our 1,000th site visit here pretty quick. So I'm going to start basically talking a little bit about the industrial Internet of Things, but in particular, I'm going to be focusing on maybe a different perspective on IIoT. I'll then give a little bit of an overview of some commercially available products, just to give you a flavor or idea of where we're headed, but I'd like to spend the bulk of our time talking through a couple of case studies that we've selected to try and illustrate a couple of distinct points. Okay. So many of you have probably seen this figure. It's been reworked into a lot of different forms and things, and we generally think of the very first industrial revolution starting in 1775 when James Watt and James Bolton patented their steam flyball governor and kind of ushered in the realm of steam power. And over the years, we've gone through different revolutions and different mega trends between, mechanization, electrification, automation, and then now into what the trend that people are defining as some form of industrial Internet of Things, cyber physical systems, however you choose to think of it. But the idea of greater connectivity and data-driven decisions looking at our manufacturing facilities. A lot of people define IIoT as in various ways, but no matter your definition, it generally involves 4 different components. We're talking about sensors and perhaps actuators to control things. We're talking about connectivity between the sensors, the actuators, and some type of data processing engine, as well as that engine that then takes that data and turns it into a usable form for decision making through to the users. The benefits are can be fairly obvious, but just to kind of iterate, we're really talking about real-time monitoring for productivity and monitoring of operations. We're talking about being able to optimize our energy usage by identifying avoiding operational challenges, as well as looking at things like equipment degradation, which leads us into preventative or even predictive maintenance of our common systems, and most of all, data-driven decision-making from the top. Okay. Now, if I start digging into IIoT and what's out there, I would say that I see two very different paradigms for how this might be implemented. We see the fully instrumented, fully implemented connectivity with new manufacturing facilities where embedded sensors are everywhere. Everything's connected through a uniform software platform. There's a lot of analytics that go into looking at how different systems interact, which is a fantastic paradigm, but we generally see it for large new manufacturing systems. But there's a lot of small and medium enterprises out there. There's a lot of places that are going to need retrofit solutions. And so I'd like to emphasize or focus on a more bottom-up approach here, at least talking about this today, and look at the opportunities that come from just selectively implementing IIoT in a limited case with low-cost or even no-cost data that you can collect, and specifically targeting energy systems that are prevalent in virtually any manufacturing facility, right? So, again, I want to give you a few commercial examples so you can kind of get an idea of where we're going. But again, please don't take this as endorsement. This is just items that we could identify on the web that kind of have kind of similar characteristics. So let's start with motors and drives, because these take probably the majority of the electrical power at almost any manufacturing facility. So as you can imagine, there's a lot of different companies out there that are developing devices to look at condition monitoring of motors. And in general, they look at things like, is the motor on or off? They may be monitoring the power signal. They may be looking at harmonics within the power to identify potentially faulty equipment. They're definitely looking at vibration monitoring, most often temperature as well. They may add in a few extra sensors for speed or other types of measurement. All of these types of systems, no matter what manufacturer you're looking for, generally have some sort of connectivity, often cloud-based, often wireless. The wireless protocols can vary, but generally feeding into often a brand-specific platform or dashboard where diagnostics can be viewed. But these are meant to be simple solutions that can be placed on critical motors at facilities with fairly low installation times that could be implemented as kind of a bottoms-up IIoT solution. If you start looking at steam systems, not surprisingly, the focus of most of the IIoT devices that we're seeing come on the market are focused on steam traps. Because, as you know, steam traps are often where you are losing the most energy in terms of failed steam traps. As we go out to sites, what we find are a lot of steam traps are in difficult to access locations. And so monitoring to see if they're in a failed state or not can be challenging. And so you're seeing devices like this that are meant to be retrofitted. They are meant to be non-invasive, so they're typically monitoring ultrasound and or temperature, often both, to try and identify if a steam trap has failed open or closed, and then provide some information through, again, often wireless communication. The wireless communication protocol, you'll see a lot of varieties, but it does matter whether, depending on what the range. Is this something where you have to get close enough that the Bluetooth on your phone will register, or is this some sort of low-raw network where you can transmit over a wide range? And that, of course, also limits how much data you can transmit. But you'll see similar systems. The common threads you're going to see are emphasis on non-invasiveness. You'll see, again, brand-specific dashboards for a lot of these things, and a fairly wide range of variety in terms of what diagnostic capabilities they're making claims to with their software. And again, often these devices come from a variety of manufacturers, okay? Including not just measuring, say, ultrasound and temperature, but we're starting to see ones that are intended specifically for flow diagnostics as well. Okay, last I want to just give you a few examples for compressed air systems, which are ubiquitous at any manufacturing facility, and often are the source of significant low-hanging fruit in terms of energy efficiency opportunities. First of all, you're seeing a lot of the compressor manufacturers come out with their own embedded solutions for condition monitoring. What you're going to find is for a premium, you can have embedded sensors. They may be monitoring pressure, power, flow to some degree, or temperature and other things. Now, I will tell you, of all the facilities I've visited, I've been to a number of these that have the embedded sensors. I have not yet been to a single facility where the plant management is actually using the data or even accessing it. The beneficiaries of this are almost always the manufacturer, who is getting information about the status of the system so they can appropriately market, repairs and other things. So that's not so much a bad situation, but it is a missed opportunity for the plant management to be tapping into this data for diagnostics. On the other hand, you also see some of products that are meant to be agnostic in terms of what equipment you're using, like these data collection modules, where you buy your own sensors, you plug them in, and then you've got a customized dashboard that you can use for data monitoring. Now, a lot of these solutions may be in the hundreds to thousands of dollars, but it doesn't necessarily need to be that way. The price of this technology is coming down quickly. On the top left here, you'll see a device that we put together in our lab just to see if we could do it for about $50 using simple Raspberry Pi that in its characteristics, except for ruggedness, match what we see on the commercial products. Obviously, it hasn't been tested under the same conditions. But you're seeing these type of agnostic data collections that could be used with customized sensors or even data loggers that simply record data that you periodically download via Bluetooth or some other fashion. So, what I'm trying to emphasize here is the idea that there is availability and growing availability of these commercially available devices that would allow from a bottom-up perspective on IIoT, and specifically targeting critical equipment at a manufacturing facility to give better diagnostics, better information about how these systems are operating, and in particular, from my perspective, energy efficiency. Now, they come with challenges. Cybersecurity is a concern. I will say, though, if all you're doing is bringing data in from sensors, there's a lot less risk than if you're actually trying to push control out, and you're not risking the control of your equipment, you're just risking perhaps the monitoring of your equipment. A bigger challenge probably is information management. How do you not overwhelm a busy plant manager with a lot of data, too many false alarms? How do you provide information in a curated way that is useful? And of course, implementation cost varies, and so the question of how to demonstrate the cost benefit for a lot of this equipment, which is why I generally am pushing for a bottom-up where you target one system with one package where it's easy to make the case, and then from there build confidence in these technologies that can be used across the plant. So, I'd like to talk a little bit about just 3 different case studies for low-cost, what I would call low-cost diagnostics. And these are probably things you've thought about or are aware of. I'll be happy if I'm preaching to the choir here. I'm going to start first with what I would consider a no-cost solution, which is simply using your plant's utility data, and give you a few examples there. Then moving to an example where we highlight the idea of leveraging existing sensors that you just may not be accessing the data from. In this case, we'll just take a simple case of a thermostat on a cooling system, and then we'll finish up by talking about compressed air systems and look at the progressive addition of sensors. So first, let's talk about utility data. So here's an example of utility data from a medium-sized manufacturing facility, and I will tell you that as we've gone to numerous facilities, again, this data by law is available to all users, but I have only been to probably, out of the hundreds we've been to, only one where the plant management was actually using this, collecting and using this actively. Again, there's opportunities that are being missed here. So for example, if you have 15-minute data, and here is an example of a month, it's easy to spot a few things that help you understand how things are working and whether you're operating in an energy efficient way. So let's start. First of all, here in Texas and a lot of other places, manufacturers are charged for peak demand. So the first thing to do is look at your demand peaks. Where are they? What's causing them? And can we avoid them? Can we be rescheduling equipment for different peak operating hours? And most probably, not insignificantly, do they match what you're being billed for? I have horror stories about daylight savings time and how you experience 1 to 2 a.m. twice in November, and the utility doubling your demand because its computer doesn't realize you're experiencing 1 a.m. twice. Okay. Second, is equipment being turned off during non-production hours? This is the production schedule of this facility is pretty obvious. What you may not realize immediately is they're using a megawatt of power during non-production times. This is way more than parking lot lights, right? What equipment is being left on that is definitely unnecessary, which I can tell you because I remember this facility. What equipment is being left on? What can be turned off? What are easy ways to reduce energy usage? Okay. What can we learn about the production schedule? Clearly here we have a plant that's operating 4 days a week. You can even spot the week of Christmas on this schedule, right? You can compare what the plant manages says are operating hours compared to what's actually being consumed to understand what does their startup and their shutdown look like. And what's happening on non-production days. And maybe even importantly, if you notice, there's an unscheduled downtime here on our second week, right? Where clearly the plant was not operating the way you would expect it to, right? Some of these things, diagnosing these things visually or simply may becomes a surprise to plant management. And then finally, if you're looking at on-site energy, this data is a wealth of useful information for understanding how solar PV or battery systems might impact your costs. Just as simple as, okay, what happens if we want to reduce our peak demand by a certain amount? What size of battery? What kilowatt capacity do we need? And what kilowatt hour capacity do we need? This data is a wealth of information that often goes unused. And even more importantly, every diagnostic thing that you're seeing here that we do can also be done on specific equipment. I'd also like to mention we have some colleagues at Arizona State University who have done some fun analysis by just simply plotting statistically the frequency that you are using power at specific levels. And what they found is the bimodal distribution can tell you a lot about how you're operating your plant, not just in terms of what type of plant you're using, you have, or what type of operation you're using, but if you take these same ideas and apply them to your biggest motor in the plant and the power generation, you can learn a huge amount about are you operating the way you think you should. Okay. Second, I'd like to talk about cooling systems. This is a project we did with a major manufacturer of cooling systems, and they asked the question, how much can you do with just a thermostat where all you know is the system on or off, and what's the set point and what's the actual temperature? Now for the sake of time, I'm gonna breeze through this, but the basic idea here is from those things, you might not think that's a lot of information, but you can start to extract a lot of information just from those things, just by looking at specific data features. Maybe not whether the system's on or off, but how is the duty cycle of the on-off cycling changing over time? Or how fast is your temperature decreasing? You look at those types of data features, and what you start to do is you can compare, using very simple statistics, what your behavior of your system is compared to your baseline. So these red contours, as you'll see, are meant to be our baseline. It's data collected over a long period of time. And what you see here is a normal system, as an example, where the blue data points represent the actual operation of the system. And what you see is no matter which data features you're looking at, it looks like it's pretty consistent. We would consider this normal. Second example, this is a system that's failing, but it's failing in a way that it's imperceptible to the users. It's essentially keeping up with cooling, but its efficiency is dropping off a cliff. Okay? And clearly what you see is for some of these data features, we're clearly outside the norm. Now in this project, we looked at AI, we looked at various machine learning technologies, and I'll tell you, they were great, but none of them outperformed simple statistical analysis for understanding what was an outlier or not. I do that not to denigrate AI, but just simply to state there's a lot of mileage to be gained just by looking at simple statistics and sensors. So what I hope you would take away from this is, if you're looking at your significant energy users, there's very often existing data being collected on the equipment, and there's a lot to be leveraged by extracting that data and looking at different features from that data to understand operation. Last example, compressed air systems. Now, these are, like I said, these are everywhere in manufacturing systems. We chose, among the various case studies we're choosing, we've fully instrumented a large system near us, where we've got 4 large compressors, and we put on a huge variety of sensors because we wanted to understand what is the marginal benefit as you start adding more and more sensing. So, for example, if all you know is whether the system's turning on and off, you can get an estimate for power. But if you add on a simple current clamp, you're not estimating power, you can actually measure your power, and you can estimate flow. Now, that may not seem really significant, but if you can estimate flow, you can start looking at how does flow change during production time, how does it change during non-production time. You can estimate what your leakage rates are simply by continuous monitoring using a simple current clamp. As you start to add different sensors, pressure, temperature, and humidity, you start to add your capabilities between what becomes estimates and what actually becomes measured, as well as combinations of these pieces of information give you multiple ways to diagnose the same problem, as well as diagnosing other things as well. So for example, using a current clamp and looking at a duty cycle and versus a pressure sensor, which can tell you, both give you ways of understanding your leakage problems, but now you've got multiple methods to correlate your data, understand how much money you can save. Similarly, you can start looking at control. How is the system being controlled? Simple visualizations help, but a lot of this stuff can be automated to provide alarms and things to the manufacturer. So, in conclusion, if nothing else, I would hope you would take away from this 4 points. 1, IIoT offers a lot of significant opportunities for energy efficiency opportunities, and I would say that a lot of low-cost or even no-cost opportunities are being overlooked. And it's easy to leverage existing data and utilizing that data, and then even the diagnostic, we can look towards AI and things like that, but even the basic statistical thresholds have a lot to offer. And with that, I'll finish, and if we have time for questions, I'll take any questions. Yes?
Several years ago, thank you. Several years ago, there was I'm talking about residential now.
Okay.
Several years ago, there was a company that would provide you a amp clamp type thing that would go on your house.
Mm-hmm.
And you have a sensor, which I put in the kitchen, to just kind of keep track of as I turn off lights or things, or the consumption of the air conditioner, etc. But there was a lot of power saved just by turning off lights in the house. You know, I mean, sometimes kids, I don't know about your kids, but
I have 6. Yeah.
but they'll leave the doors open during the middle of the summer. Right. You know, that type of thing. But it seems like, you know, the instruments you were talking about, if there was just some way, and I know maybe I'm an engineering nerd versus, you know, no normal household, but, you know, just a sensor in the house for the old man to kind of keep an eye on the energy consumption.
Yeah, and with a lot of the meters that are now on homes, you can start to access the data just like you can at large industrial facilities. Not everywhere, but it's starting to, you're seeing it in a lot of places. But I'm with you. 15 years ago, I bought several of those devices. Came with like 5 current clamps. You put it over the different fuses in your house so that I could look at my dishwasher, my air conditioner, my dryer, and from that try and deduce when things are happening and where the energy efficiency savings. So the technology is not new. It's there. But how many of us engineering nerds are taking advantage of it? Only a few.